Okay, let's talk about something that drives every Python programmer crazy. You write a loop, it seems simple, it should be fast, but it just crawls. We've all been there. Well, today we're going to dig into why that happens and how a library like NumPy can make the exact same task over 100 times faster.
Right? You've got a basic loop, maybe summing up a bunch of numbers, you hit run, and you wait. And you wait some more. You can almost hear your CPU groaning, and you're just sitting there thinking, what did I do wrong? The logic is so simple. Well, the answer is probably not what you think.
I mean, just look at this. On the left, we've got a classic Python for loop. On the right, the NumPy way. They're doing the exact same math, getting the exact same result. But that NumPy version can be over 100 times faster. So what's the secret sauce? The algorithm is identical, so where does all that speed come from?
Now, you've probably heard the usual suspects. Oh, Python is slow because it's an interpreted language, or NumPy is fast because it's written in C. And look, those things are true, but they don't tell the whole story, not even close. The real reason for this insane speed gap is actually way more fundamental and honestly, a lot more interesting.
This quote right here, this just nails it. It's all about a difference in perspective. When Python looks at your code, it sees a world full of flexible, dynamic objects. But NumPy, it sees raw, efficient blocks of memory. And that one little difference, well, it changes everything.
So get this, in Python, a number like 5 isn't just the number 5. No way. It's a whole object, a Py object that comes with all this extra baggage. It knows its type, how many things are pointing to it, its size, all of that is overhead. And when you're doing something millions of times, that overhead really adds up.
A NumPy integer, on the other hand, is exactly what you think it is. It's just the number. That's it. No extra metadata, no baggage. It's stored in a nice, neat, continuous block of memory right next to its buddies, which makes it incredibly fast for the computer to work with. And this is the aha moment. This is what's really happening inside that simple Python loop. For every single addition, Python has to go through this whole 5-step dance. Check the type of this, check the type of that, figure out how to add them, create a brand new object to hold the answer, and then update the variable. It does that 10 million times. It's no wonder it's slow.
So how does NumPy avoid all this drama? It doesn't play that game. It just takes that entire block of numbers, hands it off to a super optimized function written in C, and basically says, here, you deal with this. The entire loop runs in that fast compiled environment, and the CPU can just blaze through the raw data without any of Python's object overhead getting in the way.
Okay, so that raw memory efficiency is the foundation. But that foundation enables NumPy's real superpower, a concept called broadcasting. This is where we go from just being fast to doing things that feel kinda like magic.
So, what is broadcasting? At its core, it's a really clever set of rules that lets you do math on arrays that don't have the same shape. It's the secret to what we call vectorizing your code, which is really just a fancy way of saying you're pushing the loops out of slow Python and into that super fast compiled C code.
And here is the truly brilliant part. When NumPy broadcasts, it doesn't actually make a bunch of copies of your smaller array to make it bigger. That would be slow and waste a ton of memory. Instead, it just pretends the array is stretched. It does the math as if it were bigger, but without any of the memory cost. It's incredibly efficient.
Of course, this magic has a few rules, but they're pretty simple. NumPy looks at the shapes of your arrays from right to left. For any given dimension, the sizes either have to be the same or one of them has to be 1. If you can check that box for all the dimensions, you're good to go.
And you can see how that plays out right here. A 3x4 array and an array with 4 elements? Yep, that works. A 5x1 and a 1x6? They'll broadcast together to make a 5x6 result. But look at that last one, a 3x4 and a 3x2. That's a no-go. Why? Because you start from the right and 4 doesn't equal 2, and neither one is 1, so NumPy throws an error.
So, what does this all mean in the real world? It means you can do incredibly powerful things, like add an entire vector of numbers to every single row of a matrix, all in one line of code. No Python loops, just one clean, fast, and super readable operation.
All right, this isn't just some abstract programming trick. Let's look at a real-world example from machine learning to see how shifting your brain to think in arrays can be a total game changer.
So let's take a common task called vector quantization. It sounds complicated, but the idea is simple. You've got a bunch of known data points, let's call them codes, and you get a new one, an observation, and you just want to find which of your known codes is the closest match. So the mission is to figure out which of our codes is closest to our new observation. Now, if you were to do this in plain Python, you'd have to write a loop, right? You'd go through every single code, one by one, calculate the distance, and keep track of which one was the smallest.
But with broadcasting, we can do it all in one fell swoop. We just subtract our single observation from the entire array of codes. NumPy will automatically stretch or broadcast that one observation across all the codes, performing all of those subtractions at once in a single, highly optimized operation.
And that's the real payoff. One single line of NumPy code does the job of an entire Python loop. And it's not just that it's way faster. It's also cleaner. It's more expressive. Your code now reflects what you're actually trying to do. Operate on the whole data set, not just one element at a time.
So, what's the big lesson here? The amazing performance you get from NumPy isn't from some secret complex algorithm. It all comes down to a fundamental shift in how you think about your data.
The bottleneck in your Python code is almost never the math itself. It's the overhead of dealing with all those Python objects. NumPy gets its speed by completely sidestepping all of that and working directly on raw, predictable memory. It is literally the difference between a million tiny expensive questions and one big efficient command.
So the next time you've got some Python code that's chugging along, I want you to ask yourself a different question. Don't just ask, why is this so slow? Instead, ask, where is my loop actually running? Is it running in Python, getting bogged down in all that object overhead? Or is it running in NumPy, flying through a clean block of memory? The answer to that question is what will lead you to faster, cleaner, and just plain better code.